Hello there, my name is Grégory Bulté. I'm a biology instructor at Carleton University, and I study turtles at the Queen's University Biological Station. And I'm generally interested in anything that has to do with turtles and their environment. So I ask questions such as what turtles eat, how do they find their food, where do they spend the winter, how do they survive the winter, how do they reproduce, how do they find a mate. So this is the kind of questions we're trying to answer by studying wild turtles. I'm also interested in understanding the threats to turtles and how to minimize them, because you might have heard that a lot of turtles are not doing terribly well, both in Ontario and Canada and around the world. They're facing all kinds of threats from human activities. So we're trying to do our part in understanding these threats and, when possible, to make recommendations about how to reduce them. But today, I don't really want to talk about my own research. I will allude to it here and there throughout the talk, but really what I want to talk about is what makes a turtle a turtle. And the main thing that makes turtle turtle, and the reason why everybody recognizes a turtle as a turtle, is of course because of its shell. So this whole structure that we call the shell. So this is a remarkable structure among mammals. It's made out of bones. It has all kinds of implications for how the turtles do various things like moving and breathing, but it also has important implications for their survival. So we're going to talk about some of these aspects of the turtle shell in this short lecture. So here is a shell of a northern map turtles. And northern map turtles is the species that I spend most of my time studying. So I'm going to give a few references to these turtles throughout the talk. So the first place to start, I think the best place to start, I should say, is by giving a tiny bit of turtle shell anatomy. So you can think of a shell as two half shells, if you will. There's a back part or dorsal part, which is here. This part we call the carapace. There is also the belly part or the underneath part that we call the plastron. The carapace and the plastron are attached to one another by this little bony bridge here that we incidentally call the bridge. Both the plastron and the carapace are covered by these little plates. These plates are called scutes, and those are actually quite thin. They're a little veneer that rests just on top of the shell. And you can see this, I have another one here that is in a more advanced state of decomposition, and it's losing its scutes. So these little scutes here are starting to peel off. So scutes, you can think of them a little bit like scales, but they're different because they're resting right on top of bone. So that white stuff here that we see, this is all bone. This is the skeleton of the turtle, and we're going to talk about that quite a bit in this little presentation. So that bone is covered by these little scutes or little thin plates that rest just on top of it, and this is what gives the turtle their coloration and general appearance. So in the case of the map turtle, these little scutes have and I have the sun here, so I'll try to get a little bit closer. They have these nice little yellow lines all over the place, and these little yellow lines kind of look a little bit like a map, and that's what gives the name map turtle. So the early naturalists that described the species to Western science call them a map turtle because these little lines made them think of a map. So let's dive into a little bit more into the carapace itself. So the whole thing is the skeleton of the turtle, and that means that turtles are hauling around a lot of bones. So in our case, our skeleton makes up about 14% of our body weight. So, the rest being muscles and other tissues. In turtles, it varies between species, but it can be as high as 40% of the body weight of the turtle is bones. So that's a lot of weight to carry around. So for instance, that would be the equivalent of me having to carry a backpack every day with 40 pounds in that backpack. So that's what turtles have to deal with with having this carapace. And of course, that tends to make them a little bit slower, at least on land, because they have to carry all of that around. But there's other reasons as well why turtles are slow, and we're going to talk about some of those. So the scutes, these little scutes, they will be shed periodically. So bones is a living tissue, so it grows, and the scutes that are on top of it needs to be replaced every so often to allow that bone to grow and expand. So turtles, like other reptiles, will shed their skin periodically, and in the case of scutes, in many species, they will simply peel off. They don't do that in all species, but in things like painted turtles, like in this picture, where the turtles on the right, we see it's shedding its scutes. Now, it's not the whole scutes that come off, so when it comes off, you don't see the bone underneath. It's just the outermost part of it that comes off and just falls off in the water. So they tend to do that more in the spring and in the late summer, so after they've grown a fair bit. The other thing, because the turtle shell is a living tissue and it grows, it creates interesting things that are useful for us researchers. So turtles in this part of the world don't grow in the winter. In the winter, they just go in the water and spend the winter there. And they don't eat, so they don't grow. And because they don't grow, what happens is that they put down a little line in their carapace, or in their plastron and carapace, a little bit like the growth ring on a tree. And that is very useful for us researchers because we can age turtles using that. So not all species do it, and they don't all do it equally well at least from our perspective, but many of them do, and that's very useful. So for instance, this is a little map turtle that I caught a couple weeks ago, and you can see growth rings on its plastron. You can see them quite distinctly. So what we see in the red square here, that is the scute that the turtle would have been born with. So the turtle was born, probably came out of their nest in the spring, and then it grew during that summer. And so the first arrow you see next to the red square, that would be the growth of its first year of life. Then it went and hibernated, didn't grow during the winter, put a little line down, and then came back out. And actually this is this spring, and then it grew again this summer. So this second red arrow we see, the one that is the shorter one, this is the growth from this year. So I caught this turtle in late August. So what we're seeing is the current year growth. So it's about to stop growing for the winter. So with this, we know that this turtle is in his second year of life, which is very useful information. Unfortunately, these lines will tend to wear out, and eventually when a turtle is going to be 5, 6, or 7 years of age, we won't really see them anymore, and it's going to be difficult to age them. But at least when they're very young, we can use them to have a pretty good idea of their age, which is extremely useful for us. Now, if you recall, I said that the carapace, both the carapace and the plastron, the whole shell, is part of the turtle skeleton. And you can see the bone right here on this one. Now, if you've studied a little bit of biology, you might have learned that all animals with a backbones that live on land, so things that we call the land vertebrates, so frogs, salamanders, lizards, birds, and mammals, they all have pretty much the same sets of bones. And this is what this little figure here is illustrating. So we have the arm bones of 4 different kinds of mammals: humans, dogs, whales, and bats. And these mammals all do different things with their limbs. So the humans use them for manipulating objects. Dogs use them for walking and running. Whales use them for swimming. Bats use them for flying, and that's why they look quite different. However, if you look at the sequence of bones in these arms, you will notice that they are identical. All of them have a sequence from the shoulder to the finger that follows one bone, two bones, a bunch of little bones which make the wrist, which are in yellow, and then fingers, which are in brown or tan. So all animals with a backbone that walk on land have this sequence of bones unless they completely lost them, like snakes. But most of them still have them. And this is true for pretty much all the bones in our body. We can find the equivalent in other land animals, other land vertebrates. So that really begs the questions: if the carapace or the shell of a turtle is made out of its skeleton, where are these bones coming from? So the turtle didn't make new bones to make its carapace. It actually used existing bones in its ancestor. So we know by studying the embryos of turtles and also by looking at fossils of turtles that existed before they had a complete shell, that the shell and the carapace comes from the ribs of the turtles. So you are all familiar with our rib cage. So we have this rib cage that is very important for breathing, for instance, and protecting certain of our organs. Well, the ribs is what's making the turtle carapace, which is quite amazing. No other animals have done that. So here we have an image of the rib cage of a human skeleton. And if we look at a turtle, we can zoom in a little bit and we can see that the backbone, we can see the backbone of the turtle in the center of the diagram, and it attaches to the ribs, but the ribs, so this is a rib right here, the ribs are really big and wide. And so what happened is that when the baby turtle was in the egg, the turtle embryo was in the egg and it was developing, it started making ribs, and these ribs became wider and wider and wider, and eventually they started touching one another and they fused into one another and they created this beautiful dome that we see. So this is where the turtle carapace comes from. It comes from the ribs of the turtle. And you can see that on this diagram here. You can see, well, if you look at a skeleton of a turtle from the side, you can see that the backbone is actually completely fused with the rest of the carapace. So this is like the turtle's body is this really big, stiff masses of bone, and all the other bones are actually inside the carapace. So that is to say, all of these bones are inside the rib cage, which is absolutely bizarre when we think of it. We have this little rib cage, but everything else is sticking, is attached to it somehow. In the turtles, everything is inside and sticks out of it. And that has some important consequences for how turtles are capable of moving and breathing. So let's talk a little bit about that. So let's talk about the shoulder blade, because this is a really weird one for turtles. So you all know that our shoulder blade is resting outside of our rib cage, and we know that, we know this from looking at skeleton, but you can also feel it. If you stick out your shoulder blade, you can see them. So they're resting on top of the back of your rib cage, as shown on this little diagram. So what we see in red is the human shoulder blade. And this is true. So I mentioned that, all animals are sort of made out of the same plant. So this is true in pretty much all other land vertebrates. So whether you look at a mammal such as this beaver, you have the shoulder blade in red resting on top of the rib cage. If you look at a bird, you have the same thing. You have the shoulder blade resting on top of the rib cage. If you look at another kind of reptiles than a turtle, such as a lizard or an extinct reptile, such as a dinosaur, you will also find the shoulder blade resting on top of the ribs. Same thing in amphibians, such as a frog. So this is a frog skeleton. So amphibians don't have a rib cage, so their ribs are kind of puny. They're tiny little thing, and they don't encircle the whole body like they would do in a mammal. But you still find the shoulder blade in red on top of the ribs, so, or outside of it. Turtles though, nah, their shoulder blade is inside the rib cage, which is very bizarre. So if we take, this is a little diagram and I've showed it earlier, but I'll explain it a little bit better now. So if we take a turtle shell like this and we look at the plastron, and we were to remove the plastron and look at the other bones of the turtle, this is what we would see. We would see that diagram, and you can see the little bone in red. That is the shoulder blade of the turtle. So it's actually stuck inside the carapace, inside the shell, with all of the other bones that are associated with the limbs. So this is completely unusual, and from a developmental point of view, it took quite a bit of gymnastic in embryos to be able to take that bone that normally sits outside of the rib cage and put it inside. And researchers are still trying to figure that one out, but they're now understanding quite a bit better how this can work. And so the fact that turtles have their limbs inside, sticking out of their rib cage, make them very unusual. And there's this Japanese artist that made this magnificent illustration. Actually, he made a series of illustrations in which he depicted humans, but with bones and limbs, the proportions of what they would be if they were another kind of animal. And this is what he made for a turtle. And this is actually a really good representation of what a human equivalent of a turtle would be. So it would have this really, really big rib cage, and our limbs would be sticking out of it from holes at either ends. And you can imagine if you're trying to walk like that, you wouldn't be able to walk very fast. And that is one of the reasons why turtles are slow, because they have this very bizarre configuration of limbs sticking out of their rib cage, and that slows them down in a few different ways, and we'll mention some of them. So one of the important consequences for turtles to move to have this really stiff rib cage is that they can't bend their bodies side to side. So if you're stuck with this really rigid skeleton, you can't bend side to side, and bending side to side is pretty important for moving around. So if you look at most land animals, especially reptiles and amphibians, so think of a lizard or a salamander or a crocodile, when they move on land, they will bend side to side. And actually that bending is coming from their fish ancestors. So that's how they got, if you imagine a fish swimming, they bend side to side. So a walking lizard or salamander still has that bending motion. So that bending motion is important for two things at least. One is it allows them to reach further. So by bending to one side, you can bring that limb a little bit further and you can take greater steps, making you a little bit faster. It also keeps you balanced. So you can imagine a lizard, for instance, as a table. And like a long rectangular table. If you were to cut one of the leg of the table would probably tip where you've cut that leg. This is what would happen theoretically when a lizard lifts one of its limbs. So when they're walking, there are always three limbs on the ground and one is lifted to reach forward. When that limb is lifted, then it is imbalanced, like a table missing a leg. So the tendency would be to fall towards the limb that is lifted. However, you can compensate for that by bending your body. So by bending your body, you can shift your center of gravity and remain balanced on three limbs. So that makes their walking much more stable, that bending back and forth. Turtles can't do that. So they take short steps and they can't maintain their balance. So if you look some YouTube videos of, for instance, a snapping turtle walking, they're a pretty good example. So snapping turtles, when they go to nest, they'll walk on land and they tend to be like fairly high up off the ground. But watch them take a step forward with their forelimbs. What happens is they'll stretch their limb and they'll fall. And that's because they can't shift their center of mass to compensate for losing one contact point with the ground. So shorter steps, imbalance makes turtle slower on land. And on top of that, you have to carry that really big skeleton around. So all of this make these turtle the slow animals they are. So there's also another really bizarre thing about turtles that we need to mention about their carapace. So if you think of a mammal, like again we're looking at this beaver on all four, or if you get on your knees and all four on the ground, your elbows are going to point either to the side or backward. And you can see that in that beaver here. So this is the elbow right there, and it is pointing toward the back of the animal. And that's the typical way that land animals are built. And that's what makes them capable of effectively walking on land. Now, if you're a turtle, having your elbow pointing backward is a bit of a problem because you have this carapace that it's in the way. And you only have this hole at the front of it to stick out your limbs out of because everything else is inside. So you can't really have your elbow facing backward. So in turtles, the elbows are facing forward. So really, turtles' elbows are kind of like this. And that makes it really odd. And then their limbs have to shift backwards. So they have this really contorted forelimbs to be able to sort of work around their carapace. And again, that makes their locomotion not on land, not terribly efficient and slower. So you see that having that carapace really, really affects how a turtle moves around. But there is a benefit of having a carapace, that it is a great protection, right? So the carapace is really part of the skeleton, and bone is hard and it's covered by this also hard material that makes up the scute. So turtles have this great armor that they use for protecting themselves. So even if they're slow, they are well protected. And in fact, turtles tend to survive really well. They're survival champions, really. They can live really old because they have very few predators as adults, because even though they're slow, they're really well protected. And so you've all heard stories of turtles living for a very long time. Really, the longevity of turtles will vary between species. So there's, just over 300 species of turtles in the world, and some live shorter lives and some live longer lives. But the ones that live longer lives can live quite long lives. And for instance, Blanding's turtles can live a very long time. And that's almost a problem for researchers studying them because they live longer than the researcher themselves. So this is a good example here. There's a gentleman holding a turtle here. That's not Fidel Castro. That's Dr. Justin Congdon, who's an eminent turtle researcher. And he's been studying these Blanding's turtles in Michigan for decades. And the one he's holding in his hand was marked by another researchers in the 1950s. And it was recaptured in 2016. And it was known to be 84 years old at the time. So, of course, because of their well-protected, turtles can live a very long life. And that is very, very important for them because when they're little, they don't tend to survive so well. So the baby turtles and the eggs, they get eaten pretty quickly. So by living a long life, a female turtle can produce enough babies to compensate for all the ones that die at a very young age. So here in Lake Oppinicon, we have some turtles that we know are quite old. So those are all female map turtle basking. And some of these females were already adult females in the 1970s. And we know that because somebody at Queen's marked them. And so we still see these turtles around. So these turtles are probably in their 50s or 60s at this point. So I don't know how long they live, but I know I can at least live that long. And it might be much longer than that. And when they are past a certain size, they have a really great chance of surviving under normal circumstances. So these are 4 little map turtles that are 2 or 3 years old that I captured this just this August. And these are sort of past the stage where a lot of things will eat them. So now they have a really good chance at making it into an adult. Unfortunately, as well protected as turtles are, they are still quite vulnerable to humans, because humans use machines and that are faster and tougher than turtles. And here in this part of the world, you've all heard about cars and you've seen probably turtles squished on the road, but boats is another problem. And it's one that most people don't know as much about, because we don't see dead turtles in the water in the same way that we see turtles on the road. So it's more of a hidden problem, but it's as much as a problem, or maybe not as much, but it's definitely a big problem in some parts. So humans, we like water, we like boats. A lot of people like to go really fast on really big boats. Unfortunately, that's faster than turtle can swim, and turtles are not as tough as a boat propeller. So you end up with turtles that get hit and injured and sometimes kills, and it's something we see more and more often in many lakes in this area. So these are a couple examples. So these are two young females map turtles that had relatively fresh injuries from boats. In fact, in this lake here, one of the Rideau Lake, Lake Oppinicon, it's one now, we're at 1 out of 8 females that we capture that has some kind of injuries from a propeller. So that is really big. So imagine if you know 8 people, one of them would have been hit by a boat in its life. That's a pretty big number. And some of these turtles don't make it through that injuries. Just recently, I caught this little male here. And this is a male that we've captured, I think, for the first time around 2013, I think. Last time we've seen it was around 2018, 2019. It was perfectly fine. Caught it a couple weeks ago and had this big bad injuries on its back. It was not so bad that I think it needed to be taken to a clinic. It looked pretty alert and responsive, and there's some evidence that it was starting to scar. So I've let it go, because I've seen some turtles that are doing that can survive these injuries over the years. But that's an example, like we encounter these turtles on a regular basis. And so it's important, if we want to keep turtles around, if we like turtles as something that is part of our environment, then we will need to take some measures to limit their injuries, because the number of boats on lakes and the size of boats are only increasing. So we need, if we like having turtles as part of our ecosystems, we will need to do something about it. But I didn't want to leave you on a very depressing note about turtles. I think there's still areas where turtles are doing fairly well. I think Lake Oppinicon, despite all of these threats, we still have good evidence that there's some reproduction, as shown by these little guys here. But I think the trend is worrisome, and we should do something about it. But I want to finish by talking about turtle breathing. So you might not realize this, but your rib cage is essential for your breathing. So we have muscles that attach to it, and these muscles, when contracted, they pull on our rib cage and makes it bigger. And by making it bigger, it increases the volume of our lungs. And by increasing the volumes of our lungs, air can flow inside our lungs. And when we relax these muscles, they push on the lungs, and then we can exhale. And so breathing and the rib cage are very intimately linked. Now, turtles have this really stiff rib cage. It cannot expand and contract the same way our rib cage can. And that is a problem for breathing. So turtles had to invent a completely different way of breathing, and they actually do that with their leg muscles. So what I have here is a beautiful illustrations of a snapping turtle skeleton, and that illustration was made by Tyler Lyson's group. So Dr. Tyler Lyson is a paleontologist and is interested in turtle evolution, and he produced these magnificent illustrations. So this illustration is great because it shows the skeleton, but it also shows the lungs. So that big blue blob in there, those are the lungs of that snapping turtles. And on both sides, at the front and the back, there's pairs of red blobs. Those are muscles, and they're actually leg muscles that are used for moving the legs. these muscles are also the same muscles that ventilates the lung of the turtle. So let's look a little bit about how this works, because it is very unique. So this is a little diagram that I've taken from a book by Matthew Bonin called Bare Bones. If you're interested in animal evolution and anatomy, this is a magnificent book. And I animated that little the diagram that Dr. Bonin did to show how lungs are being ventilated in turtles. So lungs are at the back of the turtle. So they would be in the upper part of our, so on the carapace side. And then underneath we have the guts, which are in green in that diagram. And the guts are actually, so the lungs are attached to the back inside. And then below the lungs are attached to the guts. So the guts are pulling on the lungs. And they pull on the lungs, what they do is that they increase the volume of the lungs, and then they allow the turtle to inhale. When a turtle wants to exhale, it can contract its legs muscles, and that pushes the guts against the lungs, and then it pushes the lungs up and squishes, if you will, the lungs against the back of the carapace, and that forces air out of the carapace. So turtles use these leg muscles to increase their lungs and decrease their lung volume, to inhale and exhale, and they do that by pushing their guts, and basically sort of using their guts a little bit as a piston, if you want, pulling and pushing against their lungs. So this is completely unique among vertebrates. So that's the last little facts I wanted to point out about turtles and the reality of living inside a carapace. If you have questions, then I'll be available during the rest of the little sessions to discuss anything turtles, and I'll do my best to answer your question.